Hai, Assalamualaikum warahmatullahi wabarakatuh. Today we would like to present about the group assignment for BEI 2383 Power System Technology. So before I start with the introduction, let me introduce our group members. I start with me, Muhammad Fitri bin Nurdin, Nur Iskandar bin Mukhtar, and last Muhammad Said Amirul bin Samsul Kamal. So move on to the introduction. So for this assignment, we need to create a simulation based on the parameter outlined in the instruction given in the assignment question and collect the data. Based on the simulation, the green and blue arrow represent the actual power P and the reactive power Q provided to the load bus in the plane system. It is crucial to remember that the blue arrow should match the reactive power and the green arrow, diameter, and speed should show proportionally to the real power. So for compensated the load, we must integrate the capacitor. The output magnitude of the capacitor, Q cap, can be varied in 0.5 mega VAR within the preset range of 0 until 10 mega VAR. Next is to visually depict the change actual and the reactive line losses that result from the Q cap adjustment made within this range. We require to refer to the graph to determine the value of reactive power for the capacitor that reduce power line losses. To optimize the process, improving the electricity distribution system efficiency is needed. After determining the ideal reactive power for capacitor value, we are instructed to find the matching power factor at a specific point. This true analytical method make it easier to access the system performance under various load scenario, which lead to the determination of the optimal configuration with the fewest actual and reactive power losses. So that just for the introduction. So we move on to the simulation.
Assalamualaikum, my name is Muskada Mata. Today I'm going to explain the simulation for this assignment. In this simulation, we'll be using the generator, load, switch shunt, two bus, and transmission line. When we run the simulation, there are two arrows. The green arrow represents the actual power, while the blue arrow represents the reactive power. In this simulation, we only switch the value on the switch shunt reactive power. When we're increasing the reactive power on the switch shunt, the nominal voltage on the bus 2 increases. Meanwhile, the reactive power on the generator decrease. Here increases and it became 3 mega. If you increase it even further, it will become negative. As you can see here, the blue arrow decided to go different direction than the green arrow, and that is why it became negative 3 mega VAR. For the next table result, I'm going to show you in the next session. So this is the result that we get from the simulation. Our reactive power that we use is 0 to 9.7 mega VAR. There's a pattern on this result that you can see here, the actual power from the generator, 8.482 until 4.6 will be decreased. The same for the reactive power on the gen and the actual power losses, reactive power losses. After the 4.6 reactive power on the switch shunt, it increases back. As you can see here, the reason why it became negative on the reactive power for the generator, as I said in this earlier for the simulation, it goes back into the generator. That's why I have negative. It's same for the nominal voltage. After 4.6, it increases back to 13.95. Also the same for the angle, which is the same reason why I have negative. Same with this reactive power to generator. Meanwhile, for the power factor, it increases 0.863 to 1 for the reactive power on the switch of 4.6. After that, it decreases to 0.872. So for the average power factor for this simulation is 0.938927. For the reactive power cap value, which minimizes losses, is between 4.6 to 5.1. The power factor at the reactive power with minimal losses, which is 1. This is all the calculation that we have with power with general ponder denominator is 8.347. Reactive power gen 0.078. We have the angle with 0.53548 degree. And we also can calculate the power factor, and we have 0.999 is equal to 1. This is the graph that we have from the data converted into graph. You can see here, since the value for the reactive power increases only, meanwhile the power losses and the Q losses were relatively the same. And the same with the power factor and the Q cap. My friend, gonna explain even more further about the analysis of this value after this. Thank you.
Okay. So now I want to talk about the graph analysis. So for the graph one analysis, Q cap from 0 to 4.1 kVAR increasing Q cap within the specified range correlates with the consistent reduction in the both P losses and Q losses. The decline in the P losses indicate an improved power factor, resulting in the lower active power losses as the capacitor provide reactive power. Currently, the decrease in Q losses signifies the capacitor role in managing the reducing and the system reactive power losses. This correlation underscores the capacitive support positive impact on the optimizing overall power system efficiency by minimizing active and reactive power losses. So at the Q cap at 4.6 kVAR, at the Q cap 4.6 kVAR, P losses and Q losses reach minimal values, suggesting an optimal operating point where the capacitor effectively improve the power factor, leading the overall reduced power losses. And Q cap at 5.1 to 10.3 kVAR. Beyond Q cap 5.1 kVAR, P losses and Q losses rise, indicating diminishing returns in the power factor improvement and potentially contributes to increased reactive losses. The escalation in the Q losses suggests an approaching threshold. The additional reactive power support may lead an overall increase in the reactive power losses. The trend prompts a critical evaluation of the capacitor's impact at the higher Q cap values within the benefit of the power factor achievement against potential losses. So for graph 2 analysis, Q cap from 0 to 4.1 kVAR. Within this range, increasing Q cap constantly improve the power factor from 0.863 to 0.998. The capacitor introduction of the reactive power support effectively reduce the phase difference between the current and voltage, indicating a region where the capacitor bank contributes significantly to power factor correction, exchange the overall efficiency of the electrical power utilization and the reducing reactive power. Q cap at the 4.6 kVAR. At the Q cap 4.6 kVAR, the power factor achieved its zenith at 1.000, indicate an optimal operating point. This suggests that the capacitor is supplying the maximum feasible reactive power support, effectively neutralizing the reactive power drawn by inductive loads. The system attains a state of the unity power factor at the specific configuration. Q cap from 5.1 to 10.3 kVAR. Beyond Q cap, 5.1 kVAR, this is a progressive decline in the power factor. This diminishing trend suggests that the supplementary reactive power support supplies by the capacitor in the experiencing reduced effectiveness in the exchange the power factor. Possible factor contributing to this decline include system constraint or diminishing returns in the power factor correction within this range. Okay, so for the discussion, in the realm of the electrical power system, Q cap, P losses, and Q losses emerge as a pivotal parameters playing indispensable roles in the preservation of the system efficiency and stability. Q cap denoting the reactive power absorbed or supplied by the capacitor bank is qualified in the volt amperes reactive to VAR. Its primary function encompasses the equilibrium of the reactive power within the system while steering voltage levels and exchange the power factor. Capacitor banks are strategically deployed to provide or absorb reactive power, thereby optimizing system performance. P losses significant active power loss in watts includes the dissipation of the energy as the heat due to the reactive losses in the components such as a transmission line and transformers. The imperative objective lies in the minimizing P losses to augment the overall efficiency of the system. Q losses measured in the volt amperes reactive VAR characterize reactive power losses attribute to inductive element within the system. The meticulous management of Q losses assume a critical role in applying stable voltage level and ensuring the efficient functionality of the power network. That's all for me. Thank you.
In conclusion, the identification of the specific reactive power of the capacitor value, notably at 4.6, which mitigate losses and attain a power factor of 1, underscore actionable strategies for enhancing the system effectiveness. This finding offers crucial insight for the power system operators, emphasizing the pivotal role of capacitor in the reactive power management and loss minimization. This knowledge contributes to achieving a harmonious interplay between real and reactive power. And last, implementing this approach has the potential to remarkably enhance overall energy efficiency and bolster the dependability of power system. That's all for our group. Thank you.